This is the second portion of the mmWave and robotics training, which covers the technical deep dive. Topics include the steps involved in tuning the mmWave sensor configuration for a specific application, a description of the main components of the autonomous robotics with ROS for mmWave demo to understand how it works internally, and finally, a list of the most important tunable RobotOS navigation stack parameters that can be used to adjust the behavior of the robot. You may want to go back and review the first portion of the training if you have not done so already. First, let's look at how to tune the mmWave sensor configuration for a specific application. Our goal in this process is to create a mmWave sensor chirp configuration that satisfies the sensing needs of the application. TI provides two main methods for creating chirp configurations. The first is more applicable to the initial discovery and evaluation development stages and uses the mmWave demo visualizer tool described in the first portion of this training. This method can be used to quickly create and test a chirp configuration that will automatically work with the mmWave SDK out-of-box demo, which is used in the Autonomous Robotics with ROS for mmWave lab. The second method is typically used during the evaluation or design stages and uses the mmWave Sensing Estimator tool. It is a much more flexible tool that can be used to create more advanced or customized chirp configurations. However, it may require more time and effort as it can generate configurations that may not work with the out-of-box demo and instead require the creation of a custom processing chain on the device. Let's look at each method in a bit more detail. The first method uses the mmWave demo visualizer described in the first portion of this training. The link to this tool is located in the Customer Collateral section near the end. In order to create a chirp configuration, open the tool and then select the desired parameters on the Configure tab in the visualizer. Verify that the config works by sending it to the mmWave device and then review the live plots on the Plots tab. Next, press the Save Config to PC button to save the chirp config to a file on your hard drive. If you are doing this on a Windows computer, you'll need to copy the chirp config file to the Linux PC, which is connected to the mmWave EVM for the ROS labs. Chirp configurations generated using the mmWave demo visualizer can be used directly by the RobotOS mmWave labs since they rely on the mmWave SDK out-of-box demo. There are two ways to use the chirp configuration. In the first way, it's possible to reconfigure the mmWave sensor after it is already running as long as the previous config, which was used to start up the device, used the same number of transmit and receive antennas. The command to perform this is given in the ROS Point Cloud Visualizer Lab User Guide. The second method is to replace the default config so that the new config is loaded whenever the lab is started. This is required if the number of transmit and receive antennas differs from the original default configuration. To do this, place the new chirp config file in the catkin workspace /source/ti mmWave ROS package /cfg directory, which holds the chirp configurations for the lab. Next, rename the original default config file to a different name. Finally, rename the new config file to match the original default config file. The default config files in the ROS Point Cloud Visualizer Lab are named according to their configuration, such as 1443_2d.config, 1443_3d.config, or 1642_2d.config. The default config file for the Autonomous Robotics with ROS for mmWave lab is named 1443_3d_custom.config. The second method to create a chirp configuration uses the mmWave Sensing Estimator, which can create more advanced or customized chirp configurations. The link to this tool is in the Customer Collateral section. As shown in the figure, once the tool is opened, a set of inputs is given on the left-hand side, leading to a set of outputs on the right-hand side. Input parameters which can be entered include device type and number of antennas, board-specific antenna gains, regulatory restrictions like frequency range, bandwidth, and transmit power, scene parameters like temperature, maximum detectable range, range resolution, etc., and additional parameters that can be used to fine-tune the configuration. The outputs on the right-hand side include the actual chirp configuration parameters, which will need to be fed to the device itself to configure it, as well as information-only parameters, including the detectable object range at the top, as well as any errors if the configuration attempted is not valid. Chirp configurations generated from the mmWave Sensing Estimator may require a custom processing chain on the device, and thus may not be able to be used directly by the RobotOS mmWave lab since they rely on the mmWave SDK out-of-box demo. In that case, the mmWave SDK out-of-box demo code would need to be modified. For instance, if the command line interface, or CLI, rejects the new chirp config parameters, it would need to be modified to accept them, or the new chirp config parameters could be provided directly to the mmWave SDK device configuration API calls in the code. Second, the mmWave SDK processing chain would need to be modified to support the data flow, timing, and signal processing requirements for the new chirp configuration. In order to work with the RobotOS mmWave labs, the modified mmWave SDK demo must still output the same detected object data format over the UART. Now let's take a look at the major components inside the Autonomous Robotics with ROS for mmWave lab to understand how it works internally. The figure on the left shows the major components in the Autonomous Robotics with ROS for mmWave lab. The central block is the ROS MoveBase navigation package, which is part of the ROS standard navigation stack. Within the MoveBase package are several subcomponents. First, let's look at the global cost map and planner. A cost map in ROS is an occupancy grid used to track obstacles in the map. The planner is a path planner that's used to plan a path from where the robot currently is to where it wants to go, avoiding obstacles that are marked in the cost map. The global cost map and path planner are used to plot a high-level or overall path for the robot to follow. The local cost map and planner are similar, except they account for the actual robot's physical attributes, such as size and the weight, the motors, kind of the acceleration, velocities, things like that, and use that information to then determine how to move the robot to try to track the course planned by the global planner. Finally, if the robot gets stuck or cannot make it to its goal, it activates recovery behaviors. There was a recovery behavior added to this lab to clear the obstacle map and rescan when no path could be found. The ROS fake localization package, shown in the upper left of the figure, was used to allow users to set the initial location and desired destination on the map for the demo. RobotOS uses information from sensors in its path planning and collision avoidance. Odometry information is used to track the location of the robot to know where it's moved and its current orientation. Another sensor is used for collision avoidance. This can be various types of 3D sensors. For this lab, we have integrated the TI mmWave sensor as the 3D sensor for collision avoidance. Finally, the map server shown in the upper right was made static so that it can be used to define a constrained area for the robot to stay within for the demo. The RobotOS navigation stack relies on a set of parameters to control the robot's behavior. Let's look at a few important parameters that can be tuned in the demo. The RobotOS navigation stack is described on the RobotOS website at wiki.ros.org/navigation. You can look there for more information and for a description of the overall navigation stack and parameters. In the Autonomous Robotics demo from TI, the RobotOS navigation stack parameter files are located in your RobotOS workspace at the path listed in the slide. Parameter files found in this directory include costmap common params, which includes parameters for both the local and global cost maps, and then it includes specialized files differentiated for global and local. So for instance, global cost map params applies to the global cost map, global planner, and navfn global planner both apply to the global planner in the mmWave package, as well as local cost map and DWA local planner apply to the local cost map and planner. The mmWave params file includes higher level parameters for the entire mmWave package. And finally, there's a radar cost map params file, which is used to override settings in other param files. Several important tuning parameters for the local planner, which controls the behavior of the robot's physical movement in the demo, are located in the DWA local planner params file. These parameters are described in more detail at the website shown. Several important parameters involve the velocities and accelerations of the robot. The max velx parameter is the maximum forward velocity in meters per second. The ACC lim x is the maximum forward acceleration in meters per second squared. These parameters, which control the forward velocity and acceleration, will determine how smooth or jerky the forward movement of the robot is, as well as how fast it can react to obstacles. For instance, if the robot is moving very fast, it has less time to react to a dynamic object placed in its path. The next two parameters deal with rotational aspects of the robot. Since the Turtlebot 2 platform has two drive wheels, it's possible for it to turn very quickly or even spin in place. The max ROT-vel parameter is the maximum rotational velocity in radians per second, and the ACC lim theta parameter is the maximum rotational acceleration in radians per second squared. These will both determine how quickly the robot can start turning and then how fast it can spin. Finally, the XY goal tolerance is the tolerance in meters when trying to reach the goal. This is important as it determines when the robot is attempting to reach its goal, how close it feels it needs to get before it considers that it's reached its goal. If the tolerance is set to too small of a number, then if a user sets a goal that is somewhat close to an obstacle, the robot may attempt over and over to get closer to the goal while avoiding the obstacle, since it wants to avoid any collision with obstacles, causing undesired behavior instead of just stopping when it gets close enough to the goal. However, setting the tolerance too high will make the robot stop too early and not be close to its goal. The values for these parameters selected for the demo were selected through experimentation, where the robot was placed in different types of scenes with different obstacle configurations and different goals. In the Autonomous Robotics demo, the RobotOS navigation stack is set up to use a 3D occupancy grid called a voxel grid to track the three-dimensional data coming from the mmWave radar sensor. It then takes this three-dimensional grid and collapses it to a 2D cost map or 2D occupancy grid for path planning and collision avoidance purposes. Therefore, tuning the cost map parameters will affect the robot's object detection and collision avoidance performance. The cost map common params file holds most of the parameters for the cost maps, although some of them are overridden in the radar cost map params file. The parameters here are described in more detail at the website shown under section 8.2 layer specifications. Let's look at several parameters. First, we have robot radius, which is the radius of the robot in meters. This is important as it determines the path planning around obstacles so that the robot does not come in collision with obstacles. The obstacle layer parameters determine how obstacles are tracked in the three-dimensional voxel or occupancy grid. Z voxels is the number of cells in the Z or vertical axis in the 3D cost map occupancy voxel grid. Maximum value for this is 16. Z resolution is the vertical or Z resolution of the 3D occupancy voxel grid in meters per cell. So the height of the total voxel grid would be Z resolution multiplied by Z voxels. Both of these parameters will determine where the robot can see obstacles around it, since it determines the entire volume or space vertically that it will be looking and marking obstacles in its occupancy grids. Mark threshold is the maximum number of marked cells allowed in a column considered to be free, meaning that if more cells in the column are marked as occupied, then that XY grid location in the 2D cost map is considered to be occupied, and so the robot will avoid it. Obstacle range is the maximum distance from the robot at which an obstacle will be inserted into the cost map in meters. There's also a concept of an inflation layer in RobotOS, which is the distance around an object that the robot will attempt to avoid going into. The inflation radius is the max distance from an obstacle at which costs are incurred for planning paths. So therefore, when the robot is planning a path, as it gets closer to an obstacle in the cost map, it considers that area to be more and more expensive for path planning purposes, and thus tries to avoid it. The cost scaling factor is the exponential rate at which the obstacle cost for that path planning purpose drops off as you go away from an obstacle. Both of these parameters will affect the path planning of the robot and determine how close or aggressively it gets around obstacles.